All right, so in this set of notes, we're going to be starting our unit on circles. And in the first couple of lessons, we're going to be looking at some vocab and how we name objects related to circles. Some of this will be review, other parts of it will be brand new, but ultimately today, and well, at least in this first set of couple sets of notes, we're just looking at vocab in general. So we can see here that we have a diagram consisting of a circle and many lines and segments. So what we're going to jump into, there is one other point we need to add to our diagram. We're going to add it right here on this line. We're going to call that point J. He's going to be useful in a little bit. All right, so let's start with our first term. We've got our term over here on the left and the definition in the middle. We're going to be working on the naming of objects over here in the right-hand column. So that's where the majority of what we're looking at today is going to be filled in. All right, so a circle is by definition the set of all points in a plane that are equidistant from a given point called the center of the circle. So all of these points along the circle are the same distance from the center. And the center in these diagrams will be marked with a dot or a point to indicate that that's the center. If that point is missing, do not assume that it's a center. It'll be marked every time. The center will be, because it is a point, labeled with a capital letter, and that capital letter indicates what we would call the center of the circle. And when you name a circle, you're going to start by drawing a little circle symbol. In other words, a circle with a little dot in the center. And then we name the capital letter corresponding to the center. So in this case, the capital letter would be P. So anytime I see notation like this, I read it as circle P, indicating that's the center. All right, the next term equally is familiar. A radius is the distance from the center to a point on the circle. And in this case, we've got three different radii we can look at from the center to the circle. We have segment PC, segment PD is another radius, and segment PG is a third radius. Now, in this case, we're going to name all of the objects that we possibly can on your homework and quizzes, tests, etc. It's going to ask you to name at least one. So as long as you follow the directions and give at least one, you can name as many as possible, or you can just name a single one. All right, so in this case, starting at point P, we have from P to C, that segment. For now, we are naming it. It is a segment, so I'm going to put the segment bar across the top. Whenever I'm talking about how long it is, then I'm going to leave that segment bar off. We have another one from point P to point D, and we have a third radius from point P to point G. So 3 radii in this case. Now the next term that we have, this third one, is a secant line, and this is totally new to us. It's not going to be something that you're familiar with already, but it will become very useful in this chapter. It'll also become very useful whenever you start talking about trigonometry in a later Algebra 2 course and beyond. So a secant line, a line that intersects a circle in 2 points. So we're looking for a line that intersects the circle in 2 points. And in this case, we have 2 lines in our diagram. This one that intersects the circle once, and this one that intersects the circle in 2 points, A and B. So this line AB becomes our secant line. Remember, when you name a line, you name it with the 2 capital letters corresponding to those 2 points, and then we draw this line symbol above them. So to name our secant line in this case, we have A, B for the 2 points. It's the line drawn above. Our next definition is that of a chord. A chord is a segment, so here it's not a line, a segment whose endpoints are points on the circle. A segment whose endpoints are points on the circle. So we're looking for points on the circle. Here we see a chord between points H and F. Keep in mind that this segment, PD, is not a chord because point P is not on the circle. It has to be 2 points on the circle itself. So we have one here, segment HF. We have another one from G to C, and a third one from point A to point B. Now, we've already named line AB as being a secant line, and that is true. It is a line, and it extends indefinitely in both directions. But that portion of the line from A to B is still a chord. It's part of that secant line. So in this case, there are 3 chords that can be named: HF, segment GC, and segment AB. And there again, because those are segments, we'll put the segment bar across the top. So for our 3 chords, we have segment HF, segment GC, and segment AB. Now you may say, but GC, I know that to be called a diameter. A diameter, which is defined here in the next term, is a type of chord. So in this case, a diameter, a chord that passes through the center of the circle. So it has to connect 2 points on the circle and it has to pass through the center. And we can see that here in segment GC, that it in fact connects 2 points on the circle and passes through the center. So segment GC is the only one of our chords that passes through the center, making it the only diameter that we have in this diagram. Getting closer to the end here, and these two work together, so we're going to be doing these kind of in tandem. A tangent line is a line, there again it's a line, not a segment, a line in the plane of a circle that intersects the circle in exactly 1 point. And we've already seen where that is in the diagram, but we need a line that intersects the circle in 1 point. The point of tangency is the point of intersection of the circle and a tangent line. So this is the point that the line and the circle share. So to be tangent, the circle and the line must share 1 point, and we call that point the point of tangency. And we can see here that this line through points E and J is tangent to the circle at point E. That's where the two intersect. So line EJ is our tangent line, and it intersects the circle at point E. And that takes care of some of the definitions that you're going to be required to know, not in terms of being able to define it or describe what it is. It'll be simply a matter of knowing what these terms mean so that you can correctly identify them in a diagram, or when they come up in more theorems, more definitions, etc., that we're able to understand what those theorems and definitions and postulates, what they are saying based on the words that they use. So I'm never going to ask you to define these things. You're not going to be asked to state them, but you do have to know what they mean in order to be able to use them correctly. And that's what we're ultimately looking for. All right, so let's go to the back of this set of notes then and look at 3 other definitions and theorems that we're going to be talking about in this section of notes. Get that out of the way here. And the first one we start off with is the definition of congruent circles. 2 circles are congruent if they have the same radius. So let's draw 2 circles that appear to be the same size. I'm never going to judge you on your ability to draw a perfect circle. And I'm going to call this circle A by naming that point A. And I want another circle that's about the same size. That's close. And we're going to name that one circle B. Okay, so according to the definition, 2 circles are congruent if they have the same radius. In other words, if I draw a radius in circle A, and I draw a radius in circle B, they don't have to be in the same position. They do have to have the same length. So in other words, these would have to be congruent to each other. If they are congruent to each other, if they have the same radius, then we say the circles are congruent. And we write that congruent statement by saying circle A, remember how we name a circle, draw the little symbol and write the letter, is congruent to circle B. And there again, draw the symbol, write the letter. And that's what indicates that circle A is congruent to circle B because their radii are the same length. All right, the next one we want to look at is that of common tangents. And this actually involves 2 different definitions that we're looking at simultaneously. So a common tangent is a line or segment that is tangent to 2 coplanar circles. It's called a common tangent. So we need a segment that is connecting to, or a segment or a line, that is tangent to 2 circles. Now, in terms of those 2 circles, they might be congruent, but they don't have to be. So I'm going to, let's see, we're going to draw a circle here and we'll put a point at its center. I'm not going to worry about naming this one for now. And then I want to draw one that's slightly bigger. Another circle there. So a common tangent is going to be one that is going to be a tangent line to both circles. For example, maybe it connects here where it intersects both circles at one point each. One here on this smaller circle and one on the larger circle. Or perhaps it's going to be tangent to the circles by going here, intersecting this circle in one point and intersecting this circle in one point. And those give us two different types of tangents that exist, and that's what we have defined here. A common internal tangent, I'm going to underline that in pink. A common internal tangent intersects the segment that joins the centers of the two circles. A common external tangent, which we will draw in a separate color, I'm going to draw my external in this lovely purple, does not intersect the segment that joins the centers of the circles. Now notice that both of them refer to the segment that joins the centers of the circles. So in that case, let's start by drawing that segment in. Drawing a segment that connects the two centers. A tangent line that crosses or intersects that black segment will be called an internal tangent. A tangent that does not intersect it will be referred to as an external tangent. So the first tangent that we talked about, the first one I mentioned, was one where we had a line that intersects both circles, each at one point, like so. So I'm going to put a little dot over here and put a little point over here on this circle and draw the line that is tangent to both. And we'll notice there that that line does not intersect this segment. Now you might say, well, what if I drew that segment longer, then it would intersect, but that's not what it says. It doesn't say that the two lines intersect. It's specifically mentioning the segment connecting the two circles, which is not intersected by this line. So for that reason, this one is what we would refer to as an external tangent. It does not intersect the segment connecting the two centers. Now the second type of tangent I mentioned was one where it went kind of diagonally between the two circles, where we touch each circle in exactly one point, like so. So that we have, whoops, sorry, ruler got stuck to the paper. So we have one point of intersection here on the larger circle and a point of intersection there on the smaller circle. So this line does cross that segment joining the two centers, which is why it's referred to as an internal tangent. So an internal tangent is where it's going to cross the segment. External is where the line does not cross the segment. And our last theorem for today, in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So let's start with a circle. We're going to look at in the same circle first. And I want to draw two chords that appear to be congruent. So remember, a chord is a segment that joins 2 points on the circle. And I'm going to refer to this one as segment AB. And then I want to draw another chord. And I'm going to try to make it the same length as the previous one, like so, C, D. So my intention here is that these two segments have the same length. So two chords are congruent if and only if they are equidistant from the center. So let's mark the center. Now the distance from a point to a segment or from a point to a line is the distance that is perpendicular. So from this point to that segment perpendicular to it. That's what we refer to as the distance between the point and the segment. So this has to make a right angle. Likewise here, if I go from the point to the segment, there again, I'm going to make a right angle. Now, what this theorem is stating, if this distance is the same, if these two distances are congruent, then these two chords are congruent. So if the distance from the center is the same for both chords, then the chords have to have the same length. Likewise, it kind of goes in reverse order. That's where that if and only if comes up. If the chords are the same length, then these distances must be the same. So these kind of work